The math of the Tupolev Tu-154 is brutal. Between its first flight in 1968 and its gradual retirement, Tupolev produced 1,026 units. Of those, 110 were lost to hull loss accidents. In commercial aviation, we usually measure safety in accidents per million departures. But with the Tu-154, you don't need a calculator to see the danger. 1 out of every 10 planes that rolled off the assembly line ended its life as a wreckage site. This wasn't a failure of Soviet manufacturing. The airframe was actually over-engineered for strength. It was a failure of aerodynamic philosophy. The Tu-154 was designed to be the Soviet 727, a tri-jet capable of Mach 0.90 cruise speeds while hauling 180 passengers out of unpaved Siberian runways. To achieve that impossible overlap of speed and ruggedness, the engineers chose a 35-degree wing sweep. That sweep made the plane a rocket in the air, but it turned the cockpit into a high-stakes gambling hall during the landing flare. For 3 decades, pilots stepped into this cockpit knowing that the aircraft demanded absolute precision. If you missed your approach speed by 5 knots, or if you pushed the nose past a specific critical angle, the Tu-154 stopped behaving like a plane. It became a 100-ton kinetic weight, plummeting vertically while the pilots pulled on controls that had effectively been disconnected from the sky. The deaths weren't accidents. They were the mathematical tax for flying a plane that lived on the edge of a deep stall. To understand why the Tu-154 killed so many crews, you have to look at its silhouette. Like many high-performance jets of the era, it utilized a T-tail design. The horizontal stabilizers are mounted at the very top of the vertical fin. This keeps the elevators in clean air, away from the turbulent wake of the wings during normal flight. But at high angles of attack, this layout contains a lethal hidden shadow. When a Tu-154 pilot pulls the nose up too sharply, either during a botched go-around or a low-speed turn, the main wing begins to stall. As the airflow breaks away from the wing, it creates a massive wake of dirty, turbulent, low-pressure air. In a standard plane like a Cessna or a Boeing 737, the tail is lower than the wing, so it continues to fly in clean air, allowing the pilot to push the nose down and recover. In the Tu-154, that turbulent wake shoots backward and upward. At a specific angle, the shadow of the stalled main wing completely engulfs the T-tail. Suddenly, the elevators, the very tools the pilot needs to push the nose down and break the stall, are sitting in dead air. They lose all aerodynamic authority. This is the deep stall or super stall. The cold data on this maneuver is terrifying. Once the Tu-154 entered a deep stall, it was physically impossible to recover using the flight controls alone. The plane would settle into a flat, level attitude and simply drop at thousands of feet per minute. Take the case of Pulkovo Aviation Enterprise Flight 612. In 2006, the crew tried to climb over a thunderstorm. As they hit the plane's ceiling, the thin air and turbulence pushed the nose up. The plane entered a deep stall. The flight data recorder showed the pilots pulling the columns back to the stops, a desperate, instinctive move that only locked the plane deeper into the aerodynamic shadow. The jet fell 30,000 feet in 3 minutes. It didn't dive, it pancaked. All 170 people on board were killed because the plane's geometry had essentially censored the pilot's commands. The Tu-154 wasn't just stalling, it was experiencing a total mechanical betrayal where the air itself refused to touch the tail. But the T-tail wasn't the only design choice that set a trap for the crew. To find out why the engines themselves often join this conspiracy of failure, we have to look at the center intake paradox. In the West, a 100-ton trijet is a creature of paved level and well-maintained concrete. In the Soviet Union, the Tu-154 was expected to be a bus for the tundra. To understand the pilot fatality rate, you have to look at the gravel runway requirement. This aircraft was designed to operate out of Class B airfields, strips of packed earth, gravel, or low-strength concrete that would shatter the landing gear of a contemporary Boeing or Douglas jet. Engineers solved this problem with a piece of heavy machinery, the 6-wheel main landing gear bogie. Instead of the standard 4-wheel setup, the Tu-154 utilized 2 rows of 3 wheels. This design significantly lowered the ground pressure or footprint of the aircraft. preventing it from sinking into soft runways during the spring thaw. On paper, it was a triumph of rugged engineering. In practice, it introduced a brutal operational stress that killed crews through mechanical fatigue and unstable approach syndrome. When you land a high-sweep, high-speed jet on a non-standard surface, you are fighting a battle of friction and mass. The Tu-154 lacked the advanced anti-skid systems found in Western jets of the late 70s. Pilots had to manually manage braking pressure on surfaces where the coefficient of friction could change every 50 feet. If the six-wheel bogies hit a patch of soft mud or loose gravel at 150 knots, the sheer torque could, and did, cause structural failure of the gear struts. But the real killer in the gravel paradox wasn't just the landing gear, it was the foreign object damage. Because the Tu-154 sat low to the ground to accommodate its rugged gear, the three Kuznetsov engines were essentially giant vacuum cleaners for runway debris. While the two outer engines were high enough to avoid the worst of it, the S-duct center engine, engine number 2, was fed by an intake buried in the tail. During takeoff from unpaved strips, the nose gear would kick up a cloud of stones and dirt directly into the path of that center intake. A single pebble striking a fan blade at 10,000 revolutions per minute creates a blade liberation event. If that center engine disintegrated, it didn't just stop providing thrust. Because of its position in the tail, a catastrophic failure of engine number 2 often severed the hydraulic lines for the elevators and rudder. The pilot was then left in an impossible situation, a heavy jet low to the ground on a slippery runway, with no engine power and, critically, no flight controls. This specific failure chain is why the Tu-154's ruggedness was a double-edged sword. It allowed the plane to go places it shouldn't have been, which in turn exposed the pilots to mechanical risks that no amount of training could mitigate. The pilots were flying a bush plane that weighed 200,000 pounds and moved at 160 knots on touchdown. It was a mismatch of mission and machine that turned every regional flight into a high-stakes engineering test. But even on a perfect paved runway, the Tu-154 had another way to suffocate its crew. It wasn't the landing gear that failed them next, it was the way the center engine gasped for air during a turn. The Tu-154 is a trijet, a layout that provides a redundancy safety net for overwater or remote flights. However, the center engine, known as engine number 2, was not fed by a straight-through nacelle. Instead, it relied on an S-duct intake. Air entered an opening at the base of the vertical stabilizer and had to snake through a curved S-shaped tunnel to reach the compressor blades. In straight and level flight, this works efficiently. But the Tu-154 was a high-performance machine with a 35-degree wing sweep, meaning it was often flown at high angles of attack. This is where the physics of inlet distortion became a pilot killer. When a pilot pulls the nose up sharply, the air flowing into that S-duct has to turn the corner under immense pressure. Because air has mass and momentum, it struggles to follow the curve of the duct at high angles. This creates pockets of low-pressure, turbulent air, essentially dead spots in the flow. When these pockets hit the rapidly spinning fan blades of the Kuznetsov NK-8, two turbofans, they cause a compressor stall. Unlike a standard engine failure where the power simply drops, a compressor stall in an S-duct engine often sounds like a gunshot and results in a surge, a violent reversal of airflow that can physically damage the engine's internal components. The data shows a terrifying pattern. During emergency climbs or high-altitude avoidance maneuvers, engine number 2 would often suffocate first. Because the center engine is aligned with the aircraft's longitudinal axis, its failure didn't just lose 33% of the thrust, it often sent a massive shockwave through the tail structure. Worse yet, the Tu-154's electrical and hydraulic systems were partitioned across the three engines. A violent surge in the center engine could knock out the primary hydraulic pumps. If the pilot was already in a high-stress maneuver, they suddenly found the control columns becoming heavy and unresponsive. Consider the deep stall that we have previously discussed. If a pilot entered that stall and attempted to power out of it by slamming the throttles forward, the sudden demand for air would often trigger a simultaneous surge in all three engines. The S-duct couldn't provide the volume of air needed at that extreme angle. the engines would flame out exactly when the pilot needed them most. The pilots weren't just managing thrust, they were managing a temperamental breathing apparatus. If you pushed the plane too hard, it didn't just stop flying, it stopped breathing. This sensitivity to inlet distortion is why so many Tu-154 accidents involved a sudden loss of power during critical flight phases. The plane demanded a delicate touch that the physics of the S-duct simply didn't support during an emergency. But mechanical failure was only half the story. To see the Tu-154 at its most lethal, we have to look at what happened when the most advanced version of the plane met a crew that trusted its instruments too much. On April 10, 2010, a Tu-154M carrying the Polish president and 95 high-ranking officials attempted to land in thick fog at Smolensk North Airport. This wasn't a case of a broken wing or an exploded engine. It was controlled flight into terrain. A scenario where a perfectly functional aircraft is flown into the ground by its crew. This crash serves as the ultimate case study in why the Tu-154 was so unforgiving to pilots under pressure. The technical data reveals a lethal combination of altimeter lag and automation dependency. Because Smolensk was a former military base, it lacked a modern instrument landing system. The crew had to rely on a non-precision approach, manually monitoring their altitude. The Tu-154M was equipped with a Terrain Awareness and Warning System, TAWS. But because the Smolensk airport wasn't in the system's civilian database, the alarms began screaming, "Pull up," while the plane was still technically on its glide path. The pilots, likely conditioned to the nuisance alarms of older Soviet hardware, ignored the TAWS. They were using the radar altimeter, which measures the distance to the ground directly beneath the plane rather than the barometric altimeter, which measures height above sea level. As they descended, the terrain at Smolensk sloped downward into a ravine before rising back up toward the runway. The radar altimeter showed they had plenty of room because it was measuring the depth of the ravine. The pilots didn't realize they were sinking into a topographic trap. When they finally saw the trees through the fog, they slammed the throttles forward. But here, the Tu-154's momentum tax became due. The Soloviev D30KU engines on the M model take nearly 6 to 8 seconds to spool up from flight idle to full go-around power. By the time the engines provided enough thrust to climb, the plane's 35-degree wings had already clipped a birch tree, severing a portion of the left wing. The Tu-154 flipped and disintegrated in less than 5 seconds. It wasn't just a pilot error, it was a failure of the interface between 1960s aerodynamics and 21st century navigation. The plane's physical mass and slow engine response time meant that by the time the pilots realized their mistake, the laws of physics had already signed their death warrants. This leaves us with a haunting question. If this plane was such a pilot killer, why did the men who flew it defend it so fiercely? The answer lies in a counterintuitive truth about feel versus safety. In modern aviation, we are accustomed to fly-by-wire, a system where a computer interprets a pilot's input and moves the control surfaces within safe parameters. The Tu-154 had none of this. It was a purely hydromechanical aircraft. Every movement of the yoke was physically linked to the actuators. To an aviation fan, this represents the purest form of flying, but in a 100-ton jet with a 35-degree wing sweep, pure meant unprotected. Pilots often called the Tu-154 a soldier's plane. It was heavy, stable at high speeds, and incredibly responsive, if you had the muscle and the experience to handle it. However, the lack of an electronic envelope protection meant the plane would never stop a pilot from killing themselves. While a Boeing or Airbus might vibrate the stick or physically resist a dangerous pitch-up, the Tu-154 would simply follow the command until it hit the aerodynamic shadow we discussed earlier. This creates the ultimate paradox. The Tu-154 is one of the most loved aircraft by the veterans who flew it, yet it remains one of the deadliest by the data. The feel of the plane gave pilots a false sense of mastery. They felt they were in control right up until the moment the deep stall made the controls irrelevant. The plane required a super pilot, but was often operated in an era where cockpit resource management was still evolving. The cold data doesn't lie. The Tu-154 killed pilots not because it was poorly built, but because it was a high-fidelity machine that offered no forgiveness for the biological reality of human fatigue or distraction. When we look back at the top 10 deadliest models, the Tu-154 stands alone because its fatalities weren't usually the result of age or neglect. They were the result of its core DNA. It was a plane that brought supersonic-level physics to regional civilian airports, and it expected its pilots to be as sharp as the wings themselves. As of 2026, the Tu-154 has been almost entirely scrubbed from the sky, replaced by the sterile automated safety of the Airbus A321 and the Boeing 737 MAX. These newer jets are safer by every metric, with accident rates that are fractions of a percent, but they lack the personality that the 154 had. The 10% attrition rate of the Tu-154 is a haunting reminder of an era when aviation was a battle of man versus machine, rather than system versus software. It was a jet that proved that even the most brilliant engineering can become a pilot killer if it ignores the limits of the human being in the seat. 1 out of every 10 didn't make it home. That is the legacy of the Tu-154, a masterpiece of Soviet engineering that was simply too fast, too heavy, and too sharp for the world it was meant to serve.